All right, piecewise functions. Here's our foldable. As you can see, I got a little extra paper right there. You don't really want to cut it because then it cuts off one of the questions, so it overlaps a little bit, which is okay. That's fine. All right, so our piecewise functions, I don't know if you've talked about this before, but piecewise functions, let's talk about what it is first. So a piecewise function, kind of exactly as the name says, it has more than one function rule that is attached to it, and each rule has its own domain. So what ends up happening is your graph looks like pieces. So you have like little pieces of different functions, which is where it gets the name piecewise functions. So taking a look at my graph picture down here. Here is what a graph of a piecewise function looks like. This one has two different lines that are a part of it. We have this line here. So we have one piece of a line there, and then we have another piece of a line right here. Now this is still a function because even if I draw my vertical line right there, because of that open circle, it still passes your vertical line test. So these are still functions. This one passes your vertical line test because that's an open circle. If that were a closed circle, it would not be passing our vertical line test, but this one still does. So these graphs are not continuous. So these are not continuous. Continuous means that the graph is all connected. Connected. I spelled connected wrong, but I fixed it. So these graphs are not continuous because continuous means that your graph is all connected. This is not connected. As we can see right here, this is kind of like what we sometimes refer to as a jump. So we're going from this graph and then it jumps and switches to the other piece of a different function. So there's a little jump. Sometimes it's referred to as a break in the graph as well. So our piecewise functions have that space somewhere. They're not completely connected. Although you will see some that are connected in spots. So we'll talk about those examples if we come to them. So now this is discontinuous. Discontinuous just means it's not connected. So continuous is all connected, discontinuous is not connected. And to get a little bit more specific, it's discontinuous at x equals 0. So that's even specifically identifying it's discontinuous where x is 0 because that's where your jump happens in your graph here. Okay, so piecewise means there's pieces of different graphs. You could have linear graphs. You could have some quadratics in there. You could have your absolute value in there. You could have a radical. Any type of graph can be thrown into a piecewise function. It just means you have different pieces in it. Okay. So let's talk about evaluating our piecewise function. So this is actually what the equation of that last graph looks like. As you can see, we have two pieces. One of our pieces was the graph of 2x minus 1, and we had that when x was less than 0. So this is a restricted domain. Restricted domain. That one actually is 2. So it's telling us we only used that part of the graph when x was less than 0. So if I flip back for a second, that's this green. That's the green part of my graph right there. So then my other equation here, that was our other half, negative 1/2 x plus 1. We used that when x was greater than or equal to 0. So we have our function rules of our two pieces right there. So when you're evaluating your piecewise functions, what you need to do is you need to pay attention to the domain and where is that domain going to fall within your restricted domains. So f of -1 means I'm using x as -1. -1 would fall in this inequality here. It would be less than 0. So that means I'm going to plug -1 in for that x. So 2 times -1, that gives me -2 minus 1. I get a -3 for that. But then for this next part, f of 4, 4 falls in this one. 4 is greater than 0. So I'm going to plug 4 in for that x. So -1/2 times 4 is -2 plus 1 gives me -1. So you just have to pay attention to those restricted domains to figure out which rule you're going to use. All right, so f of 0, that's going to be in here because this is the one that's equal to 0. So if I plug in 0, I get a 1. So that means it's going to be 5 times 1 minus 2. So that gives me a 3. Then this one we have two parts. So -10 is going to fall in the first one. So 2 times -10 minus 1, that's going to give me a -21. So that's plus 2 times f of 10. F of 10 would fall here. So -1/2 times 10 is -5 plus 1. So that's going to be 2 times -4, which would be -8. So I get -29 as my answer for that one. All right, so when evaluating, you just have to figure out which piece are you dealing with. You look at those domains at the end to figure it out. All right, let's take a look at another one. So given this new function rule, this first equation is used when x is less than or equal to 1. This quadratic equation would be used when x is greater than 1. Let's take a look. G of -4. So that's going to fall in the less than 1 category. So that's going to be -4 minus 2. So that makes that a plus 4 minus 2 gives me a 2. All right, over here, I got a bracket. So I got to take care of the inside stuff first. So G of 1 would still fall in this first one because that's where 1 is. It's x is less than or equal to 1. That's going to give me -1 minus 2, -3, a little mental math here. G of 2 would go into here. So 2 squared is 4, times 2 is 8, minus 3 is 5. So that gives me -8 squared, which would be 64. All right. And then that last one there for the piecewise function defined below, find all solutions to the equation where f of x equals 2. So again, f of x and y are interchangeable. So really, we're looking for when y equals 2. So what we do for these ones, we're not plugging into x. We're trying to find x. So you're going to set each piece of that piecewise function equal to the y value. And then we're going to solve. So minus my 10 gives me -8, divided by -2 gives me a 4. And the other one, add a 4 is 6, divided by 3 is 2. So now we just have to check. My first piece, I got x equals 4, but 4 doesn't work in that restricted domain. 4 is not less than 0. So that's not actually going to be a solution. And the other one, x equals 2, 2 is greater than 0. So that one's going to work. So x equals 2 will be our only solution for that because, again, this piece didn't work within the domain from that function rule. All right. Then looking at our graphs, we're going to do a couple graphs here. So what I like to do for the graphs is no matter how many pieces I have, I create a table for each piece. So my first piece here, we're negative x minus 2. I create a table. The domain here is x is less than or equal to 1. So I'm going to have 1 in there. And then I'm going to pick some values less than that. Now you're welcome to use your calculator to help you make your table, or you can practice some mental math. So that's going to give me negative 1 minus 2, so that's negative 3. 0 minus 2. Negative, negative 1, so that's going to be 1 minus 2 is negative 1, and then 0. So I'm going to plot these points. All of these points are going to be 1, negative 3. They're all going to be closed circles. And I am going to put an arrow on the left side because that will keep going because it's supposed to be everything less than or equal to 1. I just used these 4 points to help me get started, but it is going to keep going over there on the left side. So I'm going to put an arrow. Now a table for the other part, this is when x is greater than 1. I am still going to put 1 in my table. I realize it's not equal to 1. I just need that point though, because I need a spot to put my open circle. And I need to put the open circle where x is a 1. So I'm still going to put that in there. So doing, again, a little more mental math. So that's going to be 2 minus 3, so it's going to give me negative 1. 4, 8 minus 3 is 5. 9, 18, so that's going to be 15. And then 16 times 2, 32 minus 3 gives me 33. No. 32 minus 3 is going to give me 29. I have no idea where I got 33 from. All right. So again, I know from my domain it doesn't actually equal 1. But I need that open circle. That's why I still put it in my table. I still need to know that value to give me my open circle. 2, 5. I can't actually plot the rest of them, but that's okay. There's going to be my other piece. I did make it curved because I know it's a quadratic, and I remember my quadratics are not straight lines. They're curves. And then you just have to label g of x. You don't need to put each part of the equation on there. If you did, you do also need to include the domain. So like if I wanted to label this as 2x squared minus 3, I would need to write the x is greater than 1 with it. And then for this one down here, negative x minus 2x is less than or equal to 1. So if you wanted to label each piece separately, you do need to include those restricted domains with it. So a table for each part is my recommendation there. Let's try one more. This one's got 3 pieces. We got an absolute value, we got a quad, and we got a constant in there. I'm going to start with my absolute value of x. So again, I know it says x is less than 1. I'm still going to use 1 in my table to get me my open circle point. So these are absolute values. That means I turn them positive. Plot my points with an arrow because that is going to keep going to negative infinity and beyond. All right. So negative x squared plus 4. So this one's going from 1 to 4. So I'm going to put 1, 2, 3, 4. So if I plug in a 1, negative 1 plus 4, that gives me a 3. 2 gives me negative 4 plus 4 is 0. Negative 9 plus 4 is negative 5. Negative 16 plus 4 is negative 12. So 1, 3, 2, 0. 3, negative 5. And then my 4, negative 12 is going to fall off. So I'm just going to kind of estimate it because I do need to have that point there. So just kind of estimate where it's going to be. It might happen sometimes that you need a point that falls off the graph. And the other example didn't matter because it was an arrow. It was just going to keep going on forever. This one, it does matter because it doesn't keep going on forever. It stops at 4, -12. So I need to at least have an estimation for it. And then for our last part, it's a constant. Your y is always going to be a 4. Our x domain, though, goes from 4 on. So again, I need that 0.44 because I need that open circle. There we go. H of x. So there's one big general. H of x is all you really need for these piecewise functions. So you're just going to graph each piece separately. And I recommend doing one piece at a time so that you don't end up with a whole bunch of dots on your graph and you're not sure which ones to connect.